Hello, Mom Aubrey here, and welcome to a new module in Earth Science wherein we will be discussing plate tectonics. So, our learning objectives for this module is first describe the continental drift theory, discuss evidences that support continental drift, explain how seafloor spreads, describe the structure and evolution of ocean basins, and explain how the movement of plates leads to the formation of folds, faults, trenches, volcanoes, rift valleys, and mountain ranges. So we will be discussing the first ever formal proposal of continental drift, a bit of historical science. Then we will be discussing its later development and its final status of how it is now accepted and how it is being used to predict and evaluate the plate tectonics of our current modern day Earth. But before we start our discussion, I would like to remind you that I have linked a podcast episode in our BBL. So it's the first item that is in our module even before this video lecture. The reason why it's the first one because it's required. So kindly listen to that. If you haven't, then come back to this lecture. So that particular podcast episode is a sort of introduction because the Nature publication has created an episode specifically to celebrate the wonder of plate tectonics. So when it is proposed, it had created a scientific revolution and it became the unifying theory of earth sciences. So if you haven't listened to that, again, kindly just go there and listen to it. If you have already listened to it, then good. You already have a quick background or review of what plate tectonics is. Okay, so plate tectonics is a very elegant set of theories or a theory which can readily explain how our Earth functions or how the continents are actually formed, how our mountain ranges are formed, how volcanoes are formed, and why do they erupt in the first place. Okay, so plate tectonics, it simply states that the Earth has plates that are constantly moving. So as you can see in this picture, the surface of the Earth is divided into little pieces or plates which moves into different directions. Okay, so the plate tectonics, however, theory has not been developed overnight. It took almost several decades of development before we arrived to the modern version of plate tectonics. So in the early 20th century, scientists realized that they could not explain many of the Earth's structures and processes with a single theory. So if you are looking at the questions of Earth science blindly, you may be wondering, even before the time of plate tectonics, the scientists are already wondering where the continents came from, why are volcanoes erupting all the time? What are the cause of earthquakes? So there should be a unifying theory which could explain all these phenomenon. So there was a challenge for the earth science community or our geologists to come up with a theory that could explain all these phenomena. So many scientific hypotheses were developed to try and support the conflicting observation. So plate tectonics is just one of the many proposals that scientists have brought forward in order to explain these phenomena. So the idea of plate tectonics states that the Earth crust is divided into 12 major plates. So I would like to highlight that it says 12 major plates. There are more than 12 plates which composes our Earth's crust. There are actually more than 50, but the major players are 12. So 12 major plates and they move in different directions. So this plate motion causes them to collide, pull apart, or scrape against one another. Okay, so the movement of these plates are what we call as tectonic. So it's like synonymous to plate movement, but specifically for the tectonics or the plates of our crust. Okay, so the word tectonic refers to the deformation of the crust as a consequence of plate interaction. Okay, so deformation of the crust as a consequence of plate interaction. Okay, so plates moving, interacting with one another, causing deformation among the plates. Okay, so again, here is a overview of the major plates. So you can see they are different sizes. So yeah, you have the North American plate, you have the Philippine plate, okay, so which is next to the Philippines. This is the Eurasian plate, the Australian plate, which is actually moving upwards. You have the Juan de Fuca plate, the Cocos plate, which is a very active plate, as well as the Nazca plate. So this area, as you know, where the Pacific Ring of Fire is located, is a very active area. You have the Scottish plate, South American, Arabian, the Indian plate, which is also another active plate. As a matter of fact, it used to be next to Antarctic before it went upwards to the Eurasian plate. Okay, so quite interesting. Tracing back the history of our plates. If you would like, I will link a video of a time lapse of the past to present movement of the plates so you can appreciate how our plates have changed in the past. Okay, so what are tectonic plates made of? So this is a review from our first quarter where I have introduced the layers of the Earth. So as you already know, the layers of the Earth are composed of the crust, upper mantle, outer core, then inner core. Okay, but there is something we call as the lithosphere. The lithosphere is a combination of the crust and the upper mantle, and that's what composes our tectonic plates. So the lower part, so you have the crust and upper mantle, which makes up your lithosphere, is on top of the asthenosphere. So the asthenosphere is the semi-molten material which is constantly moving due to the heat of the core of the core. So it's continuously moving the asthenosphere, which makes our lithosphere move on top. It's like watching ice. So you have like a layer of ice which is on top of water. So you can imagine layers of ice which are drifting or breaking apart into pieces because what is underneath the ice is not solid but actually something moving. So it's just like an analogy of how our plate tectonics work. Right. So we didn't know this. We didn't know that the asthenosphere is actually semi-molten liquid until the Cold War. So if you have listened to the podcast, it was mentioned that the Cold War. So the Cold War is a conflict between the United States and Russia. So let's just say that conflict. So during that conflict, they have threatened with one another in terms of nuclear war, and they were looking at the oceans as the venue of their war, of the battle. So the United States tasked some of its marine and scientists to survey the oceans, and more of that later because that will be very important in the next discussion or the next part of our discussion. Okay, so I like to highlight again, plate tectonics mainly means plate movement. So plates of the lithosphere are moved around by the underlying hot mantle convection cells. Okay, so I would like you to pay attention to this picture. So I have mentioned earlier that the mantle here, or specifically the asthenosphere, is always moving. So there is something called mantle convection cells, and that is particular the movement of our mantle. So it sort of circulates in different locations within the asthenosphere because of the heat from the outer core and the inner core. Okay, so you have here the semi-molten material within your mantle convection cell. So you have also locations here called ridges and trenches, which is very important in discussing plate tectonics. So the ridges are locations, so remember this, the ridges are locations on our planet where magma erupts and creates new plates. Okay, so once hot Okay, hot molten material or the magma rises from the ridge. It cools down and creates new plates. But since new plates are being formed, the other plates are going to be pushed, and they're going to be pushed back into the earth in locations called trenches. Okay, so the trench are of course cooler. So since they're old, they are older and cooler since they are from the surface. Okay, let's get a pen. Okay, they are cooler because they are from the surface. It will naturally sink as cold things sink. So they sink and then they gain heat from the outer core. Once they are hot, they start rising to the surface again. So the mantle convection cell, this particular area, the interaction between the ridge and the trench is a cycle. So it's a cycle of renewal. So new plates are being formed at ridges, while old plates or old parts of the plates are going to be plunged back into the earth to be recycled in the mantle convection cells. So that's the summary of how our plates are moving and being continuously recycled in our planet. Okay, so let's take a history lesson. So the proposal of the continental drift can be attributed to Alfred Wegener. So I'm pronouncing his name as Wegener because he's German, and he's a meteorologist and Arctic explorer. So he proposed the continental drift, and his principal idea is that the continents are made up of slabs of rock or plates, and they have drifted across the surface of the earth over time. However, originally they were all joined together as a huge supercontinent at one time. So with the continental drift theory, Alfred Wegener proposed the existence of a Pangea. So you already know this from your elementary days that the Pangea is the supercontinent that existed during the late Paleozoic and early Mesozoic. Okay, so movement of the Earth's tectonic plates caused it to break apart. So in tandem, there is the Pantalosa, which is the water which surrounds our supercontinent Pangea. So with the proposal of the continental drift theory, Alfred Wegener had mentioned like sort of a sketch. He provided some sort of map with his theory that this is where our continents came from one supercontinent within a Pantalasa, which is the ocean. Okay, so aside from that, not only he had pieced together the continents, although he's not the first one to do this, like propose that the continents were one big piece. There were cartographers or the ones who make maps. They have already noticed that some parts of the continents fit together. It's just that they couldn't explain it. That's why it wasn't proposed like in the scientific community. Now Alfred Wegener had indeed came with the map and proposed that it's because of continental drift. So aside from the map and the proposal of the continental drift, he also provided rock and fossil evidence. So he traveled different parts of the globe in order to gather evidences for his theory. So, for example, he found the fossil of Synognathus, a Triassic land reptile, in two continents, South America and Africa. Then the fossil evidence of the land reptile Lystrosaurus in India, Africa, and Antarctica. So, different types of fossils located in different continents which are separated by oceans. So you can already surmise that maybe they were once connected. That's why way back the fossils are like they were once connected. That's why all the fossils can be located in the different parts of the continents despite their current distance from one another. Okay, but unfortunately, this theory was too much, shall we say, for the scientific community back then, and the proposal of Alfred Wegener was ultimately rejected. So first of all, he wasn't very influential at that time. Okay? So there were in science there were politics as well. So in terms of politics, the Earth scientists were based in northern hemisphere, whereas most of the conclusive data came from the southern hemisphere. So there were some other proposals that the scientific community had favored instead of what Alfred Wegener was proposing. Okay. There were also possible alternative explanations to the distribution of fossils in glacial deposits. Okay, so the geophysicists could not think of a force strong enough to make continents able to plow through the oceanic crust, and Wegener assigned Pangaea for a too young age. Okay, so just to summarize this, so when Alfred Wegener proposed the continental drift, people didn't believe him because there was one big hole in his theory. What is causing the movement of the continents? I mean, imagine continents, big slabs of gigantic rock moving through oceans. What could be strong enough to do that? And Alfred Wegener admittedly said that he doesn't know. Nobody knew what is causing the continental drift. So it's like providing the result without the cause, or the effect without the cause. So without the complete explanation of continental drift, of course, scientists have to reject that. Plus, the idea that the Earth is completely, like the surface of the Earth is not completely solid, has been rejected by scientists, because during the time that Alfred Wegener proposed this theory, people thought that the Earth is completely solid. They didn't know that the mantle or parts of the mantle are actually moving or made of semi-molten material. So geophysicists back then were working on the impression that all parts of the Earth were completely solid. So with that, it just doesn't work. Continental drift just doesn't work. So his theory was rejected. But of course, as you know, one more thing. So Wegener also had made a mistake. He placed Pangaea in the Cenozoic period, or Cenozoic era rather. So he placed the Pangaea in the Cenozoic era, which is only 30 million years ago. Sorry, 66 million years ago. So that's 66 million years ago, but the real Pangaea actually occurred 250 million years ago. So there were already inconsistencies with the fossils and data records that he presented, which other scientists have detected. So with the inconsistencies plus the lack of explanation why the continental drift happens, well, it was ultimately, rejected. But as you know, it will come back and it will be later accepted as more scientists add more evidence to the theory. So we'll discuss that in the next video.